Hello, welcome. Let's try to solve another Leetcode problem, 847, shortest path visiting all nodes. So we are having an undirected connected graph. So we should know that we should always return an answer because the graph is always connected. And there are n nodes labeled from 0 to n-1. And we are giving an array of graph. So this is the array representation of the graph. And we should know about that. So where graph I is a list of all nodes connected with the nodes I by at. So this means for the node 0 index connected by 1, 2, 3, and index 1 means node 1 connected to 0, and similarly for 2 and 3 connected to 0. So this is the graph. So we're going to return the length of the shortest path that visits every node. So while we are going to calculate the shortest path, maybe we can use the BFS. Yeah, you may start and stop at any node. You may revisit node multiple times, and you may reuse edges. So that means we can reuse edges. So for example, we can visit like this. So we're gonna start from maybe node 1. We go to node 1, and then we go to node 2. And then we go back to node 0, 1 to 0 to 2, and then go back to 0, and then go to 3. So how many ways? So there are 4 ways. Maybe we can also try another way. So maybe we're gonna start from node 3, 3 to 3, 0, 2, and go to 0 and go to 1. So how many ways? There are 4 ways. Or maybe we can start from node 2. So what about node 2? So 2 to 0, and then 0 will go to 3, and 3 go to 0, and then 0 go to 1. So how many ways? So there are also 4 ways. Maybe maybe we can also start from 0. So 0 to 1, 1 to 0. There are 2 ways. And then 0 to 2. 2 cannot go to 3, 2 go 2 to 0, and then 0 to 3. So how many ways? So there are 5 ways. So this is not the best solution. So the best solution, maybe we're gonna start from node 1, 2, or 3, but we cannot start from 0. So this is just some random analysis. But for such a problem, exactly how can we do that? We cannot directly use a weighted set because there is a duplicate as is. But for the duplicate adds, can we go back and forward many times? We cannot. Maybe, for this node 1, we can go to 0, and 0 go back to 1. Can we do it again? So 1 to 0. It is not necessary. Because the state gonna be the same. Because for 0 to 1, this is a state. So let's try to check the state from 0 to 1. So this means even we use a weighted set, that is not okay for each of the nodes. Maybe we can use a mask, or maybe we can use binary numbers to represent it. So maybe we can use the bait. So for example, inside a tuple, we're gonna use the bait 1, 1, 1, 1 to represent which node is visited. So for example, 0 is visited, 1, 2, 3. So it means those 4 nodes has been visited. So if it is not visited, so we're gonna set it as 0. Now we can define the state. So we can use a bit representation to represent which node is visited. But some of the nodes can be visited many times. But how can we represent? We can use the current node with the visited node to represent a state, and this state will never have a duplicate. So for example, for node 0, for this node 0, we're gonna use 0 to represent a state, and then we're gonna use the binary representation to represent. So how many nodes has been visited? So for the node 0, for example, if we are going to start from the node 0, so this means the node 0 will be visited. So it's gonna be 1, 0, 0, and 0. I'm gonna use the so for the binary representation, I'm gonna use the first one from the left to right to represent the node 0, and this one gonna be node 1, 2, and 3. So this one, this tuple with 0, 1, 0, 0, 0, actually this just means the 0 node will be first visited. And similarly for other node, for example for node 1, it's gonna be the current node, it is node 1, and 0, and 1. So this means I'm going to start from node 1. Node 1 has been visited at this position. Yeah, so there should not be duplicate. I mean, I only have one tuple like this. I should not have a duplicate of this one. Yeah, I will explain it later. So for node 2, similarly, and for node 3. So for node 2, it's going to be 0, 0, 1, 0. And for node 3, it's going to be 0, 0, 0, 1. So this is going to represent node 3. Now let's try to use the BFS. If we are going to start from node 0, because we are not sure which value should be the best, actually we're going to use the multi-source BFS. Yeah, we're going to try all possible results. Yeah, let's just check if we are going to start from node 0, what's going to happen. If we are going to start from 0, definitely this is our weighted set. We're going to put it inside the weighted set, and then we're going to first explore the first node. It's going to be node 1. If we are going to explore node 1, we will update our state. Yeah, because before only one node is visited. Now we are going to visit this node 1. Because before that, this node 1 is not visited. But we're going to have a new state. So what's going to be the new state? So the new state is going to be this one, this binary representation. So this state going to be or we're going to use a binary or the next state. So this one or this one. What is it going to be? So it's going to be, yeah, if this one or this one, it's going to be 1, 1, 0, and 0. Yeah, if we are going to visit it, we should know that if we are going to visit this node 1, because this state is not inside the visited set for node 1 with this state. So we're going to put it inside the visited set. Yeah. So before that, we have this one inside the visited set. Now we have another state. It means in this one, only one node inside the visited set. Now we have another node. It means 0 and 1 has already inside the visited set. It means another state, but there's no duplicate. Yeah. Now what if we go back? Can we go back? Yes, because we are using the BFS, we are going to use the tuple with the current node and the at all nodes. This is the current node. This is the visited node. We're going to use the current node and visited node tuple to represent the state. And then we're going to go back to check this is 0. So what's going to 0 be like? Before that, we're going to merge the state. Yeah, before that, the state is 1, 1, 0, 0. Now we're going to use OR to merge it. So this one OR 1, 0, 0. So it's going to be 1, 1, 0, and 0. So it's going to be the weighted node, because this just means the two nodes has been weighted. It is 0 and 1. So 0 and 1 has been weighted. Because this 1 and 0 is not inside the weighted set. Yeah, because only 0, 1, 0, 0, 0 inside the weighted set, because this one is not inside. So we're going to put it inside to explore from this node 0. So this means we can go back and start from 0, and then go to 2 and go back, and go to 3 and go back. So this is actually why we're going to use the current node and weighted node tuple as the state of a BFS. Only in this way there will not be duplicate. Yeah. But for this 1 to 0, 0 to 1, can we go back? We cannot. Yeah, let me explain. Yeah, so this is why in this way we can calculate the shortest path. Yeah, so for example, if we go like 0 to 1, 1 to 0. Now, for the 0 node, we have two states. This is the previous state, this is the current 0 state. And can this 0 go back to 1? It cannot. Why? Because if it were to go back, so this value, the weighted node should merge with the current node. So 1, 1, 0, 0 or 1, 1, 0, 0, it's gonna still be 1, 1, 0 and 0, and this node gonna still be 1. So there is a duplicate, as you can see. This 1, 1, 1, 0, 0, and this 1, 1, 1, 0, 0. Yeah, it cannot be the duplicate. So this means from node 0, it cannot go back anymore. It can only go back one time. So 0 go to 1, 1 go to 0, but it cannot go to 1. Yeah, so this is why we can calculate the result. Yeah. So for example, if we're starting from node 1, 1 to 0, and 0 to 2, yeah. So this 0 can to 1, but I will ignore that because I'm gonna calculate the sorted path. And then this 2 gonna be go to 0, and then this 0 go to 3, and we can get the result. Yeah. Now let's try to define the state. I'm gonna define a variable n as the length of the graph, and this will also be the number of nodes. And then I'm gonna define an add state. So this add state will be the 1 shifted to the left n times minus 1. So this will be my add state. So for example, if there are 4 nodes, the add state will be a binary representation of 1, 1, 1, 1. Actually, it's gonna be 15. Yeah, so this will be the add state. Now I'm gonna define the queue and weighted set. Yeah, so queue, I'm gonna define it as the queue, and weighted set, I'm gonna use an empty set. Yeah. Now I'm going to check. Yeah, I'm going to put all nodes 0, 1, 2, 3. I'm gonna put all nodes inside my queue and weighted set because it's gonna be a multi-source BFS. Yeah, because I'm not sure if I'm gonna start from 0 or 3, maybe the shortest path. Yeah. So this is a multi-source BFS. So for I in reads n. Yeah. So this I just means the node 0 to n minus 1. So I'm gonna put all those nodes inside the queue and weighted set. So first of all, I'm gonna put the queue. So queue should append with a tuple. So the first one will be my current node. It is I. And then it's gonna be the weighted. If I put a node I inside, it means this I has already been weighted. So I'm gonna one shift left I times. Yeah. So it's gonna be one shifted left I times. It's gonna be like this. Yeah. So you should be familiar with the binary representation. So if this I equals to 0, it means it's just 1. If this I equals to 1, it means it is a 2. Yeah. And then I'm gonna define the steps because I'm gonna calculate the shortest time. So the steps will be my shortest path. Yeah. And similarly for the weighted set, it's gonna be the current node and the weighted node. Yeah, it's gonna be the same. Now I'm gonna check the queue. So while queue, I'm gonna pop out the tuple. It is yeah, let me divide the node as the current node as the current node, and I'm gonna define a state because this is the beta DP, yeah, with the BFS. So I'm gonna define a state, and then I'm gonna pop out the steps. So it's gonna be the q dot pop left. Yeah, so I'm gonna check if my state equal to the add state, final state. So I'm gonna return the steps. So this means the shortest path, and definitely I can find the shortest path. Otherwise, I'm gonna check the neighbors. Yeah, so for neighbor in graph with my current node. Yeah, but before I check the weighted set, I need another state. So this is only a neighbor. I need another state, so I'm gonna define a new state. So the new state would be the state or the neighbor node. So the neighbor, so for this neighbor node, I'm gonna set the bait. So it's gonna be one left shift neighbor times. Yeah. So this or means I'm gonna merge it. I think I explained it earlier. So this just means merge. We use the or operation, binary or operation to represent it. It means new state means currently more nodes will be weighted. So this is going to be the new state. Now I'm going to check the weighted set. If a tuple with my neighbor and new state are not inside the weighted set, so I'm going to put it inside. So first of all, similarly, I'm going to put the queue first. So queue should append the neighbor, and with the new state, and also with the steps plus 1, because we waited one more time. Yeah, and also for the waited set, it's gonna append with neighbor and new state. Yeah. So this is gonna be the entire code. It is not so much coding, but it's really difficult to understand. Yeah, I mean the coding is not so difficult, but understand it maybe a little bit hard, to understand, or maybe it's really difficult to think about this way to solve the problem. Yeah, so this means we have to practice more similar problem like this. Yeah, I'm not sure. Let's just try to submit. Yeah, because here I give us steps, and so this steps are gonna be starting from 0. Yeah. Yeah, as you can see, it works. Now let me submit it to check if it can pass all the testing cases. Now it passed all the testing cases and it's pretty fast. Now let's analyze the time complexity. Because we have a state, so this state, yeah, so this state will be the time for this state will be 2 to the power of n. So n is the number of the node, because we're going to use the state as the bit mask to represent yeah, all the weighted nodes. So it is 2 to the power of n. And while we are using the while loop to check the queue, we're going to check how many edges. So we're going to put all the edges inside. Yeah, so if it is a death graph, so the number of edges would be equal to the square of the number of nodes. So the time complexity would be n squared times 2 to the power of n, and this n is 12. So this means 12 squared times 2 to the power of 12. Basically, it's not a big number. I think, yeah, maybe it is 10 to the power of 5 or 10 to the power of 6. Basically, that is why this number is going to be small, and this is why it can pass. Yeah. So if you are not going to use the bit mask, yeah, if you are not using the bit mask like here, so what are you gonna do? Maybe, yeah, you're gonna put a tuple inside. I mean, put the tuple inside BFS. Maybe for the first time, it is for node 0. What do you put inside? Maybe you put a tuple of 0 inside, or maybe for the next time, yeah, you're gonna have a node 1. You're gonna put a tuple of 0 and 1 inside. Yeah, maybe for the next time, you're gonna put a tuple of yeah, maybe for the next time you visit 1, you're gonna put a 1 1 1 first inside. Yeah, but as you can see that it's the number of nodes can be really big. The number of nodes can be 12. So this tuple maybe for 0. Yeah, so this tuple can be really big. So this is 0. Yeah, so this tuple can be really big. It can be 0 to until to a big number 12. Yeah, so this makes the time complexity really big. If you are not going to use the bit mask, bit DP to solve the problem. So the time complexity, yeah. So because of the weighted set, it's gonna be really big, this number. Yeah, but while we are using a number, so actually this is just a number to represent all the different cases. So this is why it is better than the brute force method. This may be the brute force method. Thank you for watching. See you next time.